When we look at a mountain range, it looks completely still, but that permanence is an illusion. Over geologic time, the Earth's surface is engaged in a violent, continuous cycle of destruction. While tectonic forces deep underground are slowly pushing land masses upward, a counterforce called denudation is relentlessly wearing them back down. This global demolition project is carried out by 5 primary natural agents: flowing water, creeping ice, blowing wind, chemical reactions, and ocean wakes. Because each of these forces carves the rock in a highly specific way, learning to recognize their unique signatures allows you to read the deep, active history of any landscape on the planet. The most dominant carving mechanism on the continents is water. Fluvial processes rely on gravity to convert the potential energy of rain falling on high ground into kinetic energy, giving streams the mechanical power to excavate rock as they flow downhill. In steep highlands, this rushing water cuts straight down, creating sharp, V-shaped valleys. As rivers reach flatter lowlands, they lose speed, weaving into winding, meandering channels and looping oxbow lakes. This satellite image of the Nile Delta shows the sheer scale of fluvial deposition. Rivers are responsible for delivering up to 90% of all continental sediment into the ocean, building massive, sprawling green structures that push miles out into the dark blue water. Where water freezes, gravity employs a different tool. Glaciers are massive, slow-moving rivers of compacted ice that act like terrestrial bulldozers, scouring the bedrock through intense grinding and plucking as they inch forward. Looking at this coastal fjord, you can see exactly what an ice bulldozer leaves behind. The glacier has hollowed out a narrow V-shaped river valley, replacing it with steep, vertical rock walls and deep water that form a massive, distinct U-shape. When those glaciers finally retreat and melt, they dump everything they were carrying. In this image, you can see the resulting landform, a moraine. It's a chaotic, unsorted mound of gray, rocky debris left sitting directly at the base of the white ice mass. Together, water and ice serve as gravity's primary engines, mechanically tearing the continents apart and hauling the debris down to sea level. In arid environments, water is scarce, leaving wind as the most constant physical force. Yet counterintuitively, the occasional, violent flash flood still performs the heaviest lifting of desert erosion, quickly washing away dry soils that lack plant roots to hold them in place. Between those rare floods, wind takes over through saltation. Instead of lifting a sand grain into the air indefinitely, it skips along the surface. When it hits the bed, it ejects other grains, creating a bouncing chain reaction that builds massive dune fields. Some landscapes aren't shaped by mechanical force at all, but by chemical decay. These are karst systems. When rainwater falls, it picks up carbon dioxide, becoming slightly acidic. As this weak acid seeps into the ground, it slowly eats away at soluble carbonate rocks, like limestone, carving out vast, invisible underground drainage systems and caves. We only see the results of this chemical decay when underground structures collapse. This photograph from a karst region shows exactly what that looks like. Steep, isolated limestone towers covered in vegetation, left rising abruptly out of a flat valley. Both arid and karst environments prove that you don't need the heavy force of a rushing river or a glacier to sculpt a continent. Persistent wind mechanics and invisible chemical reactions achieve the same massive results over deep time. Eventually, all land meets the ocean. The coastal zone is a high-energy boundary where the constant pounding of waves, the pull of tides, and the sweep of longshore currents. In this image of an erosional coast, the evidence of that extreme hydraulic action is obvious. The energy of the waves has smashed away the weaker material, leaving behind jagged cliff faces, resistant rocky headlands, and a pile of broken boulders. But that eroded material doesn't disappear. It gets pushed along the shoreline to create depositional coasts, where an abundant supply of sediment allows the ocean currents to build entirely new landforms like beaches. This diagram shows ocean currents engineering new coastlines. First, longshore drift carries sand outward, forming a narrow spit. In the final panel, a storm surge violently breaches that spit, creating a fully formed barrier island separated by a new lagoon. Because they are driven by the daily rhythm of tides and the erratic violence of storms, coastlines are the most rapidly evolving environments on Earth, constantly being erased and redrawn. We often think of geology as ancient history, but these 5 sculptors are actively carving the planet right now, directly beneath our modern cities and infrastructure. Our survival relies heavily on their byproducts. Fluvial floodplains provide the nutrient-rich soils that support global agriculture, and porous karst aquifers filter and store vast amounts of our daily drinking water. Living on a constantly shifting canvas comes with intense vulnerabilities. As global temperatures increase and sea levels rise, the hydraulic energy pounding our coastlines accelerates the erosion of the land we've heavily developed. At the same time, shifting climate patterns alter precipitation, forcing arid, wind-scoured landscapes to expand into areas that used to hold fertile soil. Understanding how water, ice, wind, chemistry, and waves operate allows us to anticipate the landscape's next move. It gives us the data to predict where it will be safe to build our future on a planet that is never truly finished.